ठीक है. Proceed.
Okay, so good morning. And can you see all this? Why it is coming here? Okay. So good morning. Today we'll be discussing on Lifshitz transition and a non-Fermi liquid behavior in highly doped semi-metal. So it is not moving forward. Yes. So usually, as a condensed matter researcher, if one is interested to explain the metallicity of a material or a semi-metal, then one has to take into account the Fermi liquid theory and Drude models, which is very famous and a textbook description of the metallicity. And this is what the expression is. When tau is the relaxation time, it is the scattering between electron scattering rate, which is proportional to the quadratic temperature dependence. So that is why if you see the resistivity of the material, it usually varies as the exponent, which is equal to 2. So a quadratic temperature dependence of the resistivity is expected for the metal. This expression is based on merely on the Fermi liquid theory and the Drude approximations. However, in some metals or in some system, it has been found that the exponent is actually not dependence quadratically. It instead lower than 2. So in order to explain the physics why it is lower than 2, two proposed mechanism has been theoretized. One is quantum fluctuation around the critical point. You know the quantum fluctuation, it is a quantum mechanical term. And the critical point, it is the point at which the transition occurs or order parameter diverges as such. And then another mechanism is Lifshitz transition involving the critical band structure modifications. What does it mean? A Lifshitz transition, as I have defined below, it is the topological change of the Fermi surface. And you know why I have to straight away get into the Fermi surface? Because you know in a Fermi liquid theory, it is the highest occupied energy band at absolute zero temperature, which is known as the Fermi level or Fermi surface if it is two-dimensional in nature or three-dimensional in nature. And it can be modified by different external stimuli, such as electromagnetic field, of course, by strain and doping and pressures. So this kind of modification of the Fermi surface is proposed by Lifshitz, and then in a journal, it is known as Lifshitz transitions. It has some topological origin. That is why they are calling it to topological change of the Fermi surface. But the problem is, though this mechanism has been proposed in order to explain the non-quadratic temperature dependence of the resistivity in some of the metals and the semi-metals, we will discuss one of those, the case study. But the quantification is very difficult. And the quantification is very difficult. The reason is the presence of all these contributions. I mean, if you look at the material where there is a antiferromagnetic transition occurring along with the spin fluctuations or a temperature dependent spin orbit coupling in high atomic number element in a compound or metals, or thermal expansion with interlayer interaction variations and thermal excitation effect. I mean phonon and all those interaction. But in this paper, the author have tried to quantify the physics. I mean two proposed mechanisms, this quantum fluctuation around the critical point and Lifshitz transition. How could this thing be quantified and explain the non-quadratic dependence of the resistivity on the temperature? So the material under investigation is niobium selenide, which is a monoclinic in structure. It is a layer material and it is semi-metallic in nature up to 30 Kelvin, and above 30 K it is metallic in nature. So look at this figure A. Inset shows the single crystal of niobium selenide, which has been prepared by the chemical vapor transport method. And this peak you can see in this is 00 n index. I mean 00 L is perpendicular. It is along C axis only. You can see all the HK indexes are 0. However, L index is finite. And that is why it is 00 n index, we can call it in the language of structural analysis. And the figure B, and this high intense peak clearly shows it is a single crystal in nature. Okay. And in figure B, it shows the high angular annular dark field image of scanning tunneling microscopy. And this is the interlayer distance. And this is how the arrangement of niobium and selenium is. And this is the Miller indices of the directions. And as I have mentioned earlier, this is a layer material. You can see the layers. It is the scanning electron microscope image, SEM image, which clearly confirms the layer structure of the materials. So now coming back to the figure D, inset you see, the upper inset. This is the transition. This is the magnetic transition, resistivity, where it actually shows the superconducting transition at a 2.4 Kelvin. You could have seen it in liquid helium case with the very famous superconductivity transition at a 2.4 Kelvin. And the lower inset is the Hall probe and Hall bar. It is nanometer thickness, 20 nanometer thickness of niobium selenide. It is the Hall bar arrangement where Hall measurement have been carried out. And this is the resistivity during the cooling and heating procedure. Then this is the structural description of these materials. And how about non-Fermi liquid behavior? Just for the sake of elementary understanding of non-Fermi liquid behavior, the material which doesn't obey the Fermi liquid behavior, the immediate occurrence of this claim is resistivity has to vary as a second power of the temperature, or it's a quadratic function of temperature. Rho has to vary as a function of temperature quadratically. If it is not varying quadratically, then it will be considered as a non-Fermi liquid behavior. And along with that, you can have a different specificity variation, different magnetic transition variation, and many more other physical parameters which will have a different dependency on the temperature as compared to the Fermi liquid systems. So basically here the emphasis is on a transport property. That is why they have extensively investigated on the resistivity. If you see the resistivity, this is the resistivity plot of this niobium selenide material as a function of temperature, and they have done it up to 30 Kelvin. Why 30 Kelvin? Up to 30 Kelvin there is one regime, and above 30 Kelvin there is another regime. So here in resistivity, if you see, and this is the equation have been fitted. You see, this is the very famous equation. You know, this is ρ0 is the temperature independent resistivity, which is the origin associated with the defect or impurities as present in the system. And this is the thermal expansion coefficient alpha, and this is the exponent beta. And it is the temperature. You see what is the value they have obtained. They have obtained the value of 1.80, which is way below 2. So definitely this clearly confirms that the system is not belongs to the Fermi liquid theory. So the physics is definitely not following the Fermi liquid physics. However, when they have obtained the resistivity and obtained the value of beta, and how does it vary as a function of temperature? You see the exponent beta varies as a function of temperature like this. Up to 30 Kelvin, beta remains 1.8. However, after that, it was supposed to be up to 2. But instead it is found to be 1.8. And above 30, it is even smaller. It is even smaller. You can see the value is further declined. And what is the reason? That's what we're going to explain further. And what is the origin of this? So if you see this, as I was telling, 2 experiments have been
Professor,
yes.
in the last slide,
Ah,
that blue region is written non-Fermi liquid, right? That pink region is also non-Fermi liquid, or it's another view?
Where? This one.
You have divided 2 parts now. One is blue part, one is pink part. The red, left, right side is pink, and that is both.
All these things is all this region are non-Fermi liquid. I told
The
you,
whole reason is NFL. Okay, okay.
had it been Fermi liquid behavior, it would have exponent beta
2.
equal to 2. Okay.
Okay.
But you can see there is a significant deviation, and at a particular temperature, they have shown it varies at 1.8. You see
Okay.
now, up to 30K, it varies up to 1.8. So
Okay.
above 30, the value of beta is even smaller, because you can
Okay.
see how has it varied. And
Okay.
we'll discuss further where has this coming out of.
Okay. Okay.
Sorry. So here there are two experiments they have investigated extensively. One is magnetoresistance, another one is Hall resistance. Magnetoresistance will give you a claim where the Lifshitz transition, I suppose you understood it. It is the opening of the Fermi surface, because in closed Fermi surface to open Fermi surface, you would have encountered this Lifshitz transition in wild semi-metal. Often you would be seeing in the literature. So closed Fermi surface to open Fermi surface due to the external parameter is known as Lifshitz transition, sort of. So here this NH and Ne, it is nothing but the hole density divided by the electron density. And you know what is the measurement you need to carry it out in order to get the carrier density in a metal or semi-metal. That is the Hall resistance, right? You see up to 2.4 Kelvin, this is the superconductivity region. You don't need to worry about this. That is why the investigation have been carried out starting from 5 Kelvin, so that you should get rid of the contribution from the superconductivity. Okay, so that is why you can see how this ratio varies from 5 to 30K. Suddenly you can see there is a significant enhancement at 30 Kelvin, and this yellow double-headed arrow indicates the temperature at which the Lifshitz transition occurs, or where the topology of the Fermi surface really changes. And this coexistence of a hole and electron and a dominant of a hole, I will explain why they are explaining in this way. Likewise, this is the mobility, and you know from where, which measurement will give you mobility. Mobility, you can Vd equal to mu E, and the moment you know the magnetoresistance and the Hall resistance, you can easily calculate the mobility. And this is how the mobility changes. Suddenly at the 30K, you can clearly see the sharp gradient, sharp fall. So again, it also supports the claim. This is the temperature at 30 Kelvin. There is something serious happening to the Fermi surface. Because why regularly I'm repeating Fermi surface? Because this is the surface, or this is the energy level where the charge carrier predominantly decide the transport feature of the material. You know it is the trademark assumption, or the presupposition in the background of the Fermi liquid theory proposed by Landau.
Kyanti,
Yes.
so in these plots where you are showing NH over NE and mu H
Yeah.
over mu E,
Yes.
so why is there a region? Why you are not showing us a line or a plot? Why is there a region? What does region mean?
I mean, you want to this red region, or this?
Yeah, this red region. So why you
Yeah.
don't have a line or a plot? Why do you have a region there?
Yes, that's a very good question. Actually, region indicates the error bar.
Okay, fine. Okay.
Bar. One is Rahul bhai, associated with the geometry of the Hall bar. The Hall bar I have showed you in the inset. So some geometrical error associated with geometry would be there. Another one will be this. This thing, this hole and the electron. It goes under the name of two-band Rhodes model. Two-band Rhodes model. One band for hole, one band for electron, and the error associated with that, because we are actually deriving it from that fitting. So the error associated with both geometry as well as this two-band model.
Okay. Fine.
Now coming to the figure C, this is mind it, this is the temperature at which the Lifshitz transition occur, or the topology of the Fermi surface happens. And coming back to this magnetoresistance, this is known as magnetoresistance. You know, it is a change in resistivity as a function of magnetic field divided by the zero field resistivity. as a function of quadratic dependence of the magnetic field. Okay, this T is not temperature, so please do not get confused. This is associated with the, I think, Tesla square. Okay. Yes, I think Tesla square, not temperature. It's Tesla square. So if you see, if you see from 5 Kelvin, 10 Kelvin, 20 Kelvin, and 30 Kelvin, you see this quadratic feature as slowly becoming linear at 30K. And above that, it is clearly it is 30K. Okay, at 30K it become linear. So what is the physics? The physics is, if a charge carrier associated with a single band and that charge carrier has a single relaxation time period, then you expect the magnetic resistance, this delta rho by rho zero, has to be the quadratic function of the magnetic field. This is associated with the relaxation time of the charge carrier taking part in the transport, provided it is situated in a single band and associated with the single relaxation mechanism. But if it doesn't, if there are multiple relaxation time is associated with it, along with the multiple bands, then you don't expect this usual behavior. But again, you see, I just want to emphasize at 30K, you don't see quadratic temperature dependence of magnetic resistance. Instead, you see linear magnetic field dependence above 30K. So that says at 30K, again, Fermi surface topology changes, which is further support the claim of this Lifshitz transition at 30K, which we already have seen it from magnetic Hall measurement. And another figure D, it is known as Kohler's rule. Kohler's rule is actually mu0h, the magnetic field, multiplied with relaxation time. It should actually scale to one universal plot. If it is associated with single relaxation mechanism, associated with a single band, then all this magnetic resistance plot should fall one over another irrespective of the temperature, if they are actually associated with the single relaxation mechanism. Okay. Now you see delta rho by rho zero, very same thing. Instead of quadratic function dependence of magnetic field, this is nothing but mu0 by rho zero. And 1 over rho zero is nothing but the relaxation time. So mu0h into tau or mu0h by rho zero. You see up to 30K, they actually 30K and above, they all are fall over one another. Okay. But below 30K, you see they are not falling over one another. So that means below 30K, there are two band mechanism is present. That means the contribution from hole as well as electron wave packet is finite. However, above 30K, there is a single band contribution. And to be precise, you can see above 30K, it is only hole is dominating. But below 30K, up to 5, hole and electron both are dominating. That is why I told you, if a charge carrier is associated with the multiple band and multiple relaxation mechanism, then they don't follow this Kohler's rule or they don't fall over one another. That is what exactly you can see one to one. And this is the first principle calculation of the niobium selenide, as I have told. This is the single unit cell of that. And this is the electron pocket and the hole pocket. It is also calculated from the first principle band theory calculations. So from this, the conclusion is at 30K, topology of Fermi surface really does change, and relaxation mechanism associated with the charge carrier below 30K and above 30K are distinctly different. So now you see, it is the first principle calculations of electron and hole density. We have here calculated, the ratio. And from here, you can precisely actually calculate the exact number density of charge carrier. So up to 2.4 Kelvin, we are not bothered about. We are short up to 5 or above 2.4 to 30K. You can see there is a finite hole density of state and the finite electron density of state. And how much, what is the density? 10 to the power 19, 10 to the power 21. But as you increase the temperature, there is a chemical potential shift, which is temperature dependent. And the whole carrier became 10 to the power 21 to 10 to the power 22. It's sort of a highly doped region. So at 30K up to 2.4K, it is a semi-metallic because they are actually touching one another. Here it is highly doped region, it is becoming metallic and it is hole dominated. Now you see, this is exactly the band theory calculation. And again, this bar you can see, it is of course error bar. In addition to that, this is the calculation done by using first principle. And this whole, this circles, white circles and this pink circle, these are actually the experimentally obtained value at a particular temperature. So you can clearly see they're well within the error bar as well as they are following the trend as per the theory. And what is the chemical potential shift? Nearly 30 milli electron volt shift is there, nearly. And this is the two band Edwards model, which is very elementary. You all are familiar with. N is the electron charge carrier density, and E is the charge, and mu the mobility, and this is the corresponding counterpart associated with the holes. Now, what we'll do here? This is the equation. We will try to fit it. So when you use to fit it to obtain the exponent, and what was the initial claim? Initial claim was, if you find the critical exponent of this beta less than 2, it is the confirmation that it probably not following the Fermi liquid behavior. It is non-Fermi liquid behavior. If it is following non-Fermi liquid behavior, what is the possible origin? So here you see, this is the equation. They have tried to fit it up to 5 to 30 Kelvin, up to 50 Kelvin. You can see up to 30 Kelvin it is fitting quite well, and then above 50K it is varying. See, this is beta E and this is beta H. What does it mean? You can, so beta is only electron. If you use this only this equation, if you assume that in this region only electron is contributing, and what is the possible beta value you can end up with? You can end up with the beta value 2.47. But remember, you please don't forget this value. This is our reference. This is our experimental data. We got 1.80. Okay, 1.8. So now you see, if you assume only electron density of state is present and it is contributing, then you will end up with the beta value 2.47. If you only consider a hole present in it, you will end up with 1.67. So neither of these two is actually anyway closer to 1.8. So though whole contribution 1.67 and that is 1.8, but still there is a significant deviation. But assuming only electron is way different, 2.47. So what is the conclusion? Conclusion is you use the contribution from both the density of states, electron as well as holes. And what is the value you have ended up with? 1.79. And what is the experimental value we have obtained? 1.80, which is actually very much close to the obtained experimental value. So what is the conclusion? Conclusion is here probably both the charge carrier, electron as well as hole, contributing to the transport mechanism. That is correct. That is correct. 1.79. You see, only hole it is 1.67. The B total is 1.79. There is a significant deviation up to 30K. So here, that is why up to 30K, they have assumed that it is two-band model. Two-band means both electron and the hole are contributing. But above 30K, they are getting even smaller value than that. So they are assuming 1.67, the value they have obtained, and that is why they have considered here after 30K, only hole is dominating. So after 30K, the system becoming metallic. Below 30K, it is becoming semi-metallic because two they are called as pockets, electron pocket and hole pockets. And the point at which they actually touches, it is semi-metallic. You know, by the elementary definition of semi-metallic, semi-metal, two band touches at a single point. Okay. So and where this topology changes, or you can see the electron pocket and the hole pocket on the Fermi surface. Actually, it is a non-differentiable point in the momentum space of energy momentum relation or a dispersion relation. It is otherwise known as Van Hoff singularity. So the claim is here total resistivity is 1.79. We obtained by using two-band Rhodes model, and contribution is from both the orbitals, electron and hole packet. So, what is the reason behind it? Why it is happening? It is happening because the chemical potential shift is happening. Here you see this much electron density of state was there up to 30 K. But and where was the chemical potential? The chemical potential was here, total line. But when you increase the temperature, it falls down. So whole density of state has increased. You can see here, but the electron density of state nearly became empty. So that is the reason why you are getting this. So the finding is, the home tech message is, the non-quadratic temperature exponent for an electron and hole could make a quadratic temperature exponent. One can ask the question, okay, if you take the two-band model and you are very much getting the exponent to which what you have obtained experimentally, beta total 1.8, then why individually you are trying to do this? Why? That is the reason. Because one can have non-quadratic temperature exponent for electron and for a hole separately, but when you put them together, they can have actually quadratic temperature exponent resistivity, and you may mislead, actually you may misinterpret that probably this is also following the Fermi liquid behavior, which is wrong. That is why they have separately tried to fit it and see whether they have they have the individual exponent anywhere closer to Fermi liquid. No. So this is the first ever quantification of this claim, the non-trivial chemical potential shift by temperature change, supported by first principle calculation and two-band analysis of the hole and magnetic resistance measurement, was successfully used to explain the Lifshitz transition and non-Fermi liquid behavior in the niobium selenides. Thank you.